Hi, I'm Bob at airdensityonline.com. We're going to talk about mechanical fuel injection and turbochargers. We have two profiles selected from our list. One is Turbo 2000 HP No Boost, NB, and the second one is Turbo 2000 HP 2B. That's 2 atmospheres of boost. Those have already been loaded into the ProCalc baseline profiles. This has been set up for a 500 cubic inch V8 engine, and we had to go to a 9 gallon a minute fuel pump to make this all work. It's 8 cylinders, 1 nozzle per cylinder, and this particular combination, which we developed with ProCalc, uses an 80 thousandths main bypass, and then there's an additional bypass which is 190 thousandths, and these are the nozzles. This combination in approximately sea level weather gives about a little over a 5-to-1 air to fuel ratio. And that's again for a 500 cubic inch engine with turbos that are basically idling. Now when we go to boost, we have to go to a richer air to fuel ratio. Now let's examine this setup. In this setup, all we have to do is for 2 atmospheres of boost, we double the engine size, so from 500 to 1,000 cubic inches. Again, here's our same fuel pump volume, our 8 cylinders, 1 nozzle per cylinder, our 80 thousandths main bypass, and all we do is drop out the second bypass. And dropping that bypass out under boost and at 2 atmospheres of boost with the same nozzles gets us slightly less than a 4-to-1 air to fuel ratio, which would be appropriate for turbocharged methanol. It's a real simple setup. 1 set of nozzles, 2 bypasses. You drop 1 bypass off for boost. Using ProCalc, all the nozzles and bypasses are adjusted to get approximately a 5-to-1 air to fuel ratio for methanol at sea level with that jetting, and about less than 4-to-1 under boost for 2 atmospheres. And these were developed for sea level weather, and they could all be adjusted and changed for different altitudes if necessary. We're going to further examine this with one of our calculators, in this case the air to fuel ratio calculator. We've gone ahead and loaded current weather into this calculator. Now we're going to go ahead and get air to fuel ratio. Okay, this is a summary of all of the data that the air to fuel ratio calculator has produced. This is the uncorrected barometer. This is the density altitude from the temperature barometer and humidity that we put in. This has an air density of 95% and water grains of 30. The jetting combination at 8,000 RPM has a 3.94-to-1 air to fuel ratio, which is approximately right for about 2 atmospheres of boost. That's about a 2,000 horsepower engine if it starts out 500 cubic inches. And the fuel pressure is about 193 psi, and that's all done with a 9 gallon a minute fuel pump. In addition, there's target RPM values, and the target RPM can be changed so that you can get different pressure values at different RPMs, and you can actually go all the way down to idle speed and find out what your idle pressure is with different combinations. One of the key things with ProCalc is that there's a data output called get CSV data, or comma separated values data. That is a standard format. What we have here is a display of a spreadsheet program with fuel injection data from our ProCalc jetting calculator. We've exported the data from the calculator and imported it into an Excel spreadsheet. This particular display shows in column A all of the entries that are in the calculator. Each field that appears in the calculator screen shows up here. In addition, the data for that particular profile is displayed here. Now this is the normally aspirated profile, which I've labeled NB. The other profile is 2B for 2 atmospheres of boost, and all that data was exported and then imported into this spreadsheet alongside the previous data display. Now, key features of this are in the normally aspirated mode, it's 500 cubic inches, and in the boost mode, it's 1,000 cubic inches. Keep in mind this could be it could be 750 cubic inches for, say, a lower boost level. It can be more than that for a higher boost level. You can simply adjust the engine size in the ProCalc calculator, and it will recompute the air-to-fuel ratio for that nozzle combination. What we did was adjusted nozzles until we got the air-to-fuel ratios and the fuel pressure targets that we were after. Going back to the normally aspirated mode, here's our weather data that was exported here. This is again, close to sea level data. And then our air-to-fuel ratio, again, approximately 5:1, is what our targeted value was. The cells were yellow highlighted wherever there was a change from the previous data. So again, up here we changed the engine size from 500 cubic inches to 1,000 cubic inches. I yellow highlighted that to show that there was a change. That's an Excel tool. Changing the nozzles and changing the main bypass situation allowed us to get a richer setup. And then this was the fuel pressure maxed out for this combination. This shows the target RPM, and it shows our main bypass in this case, and then a high-speed bypass which is dropped out for boost. We show that as a yellow. These are our nozzles, and this setup is similar to the one that was shown in the ProCalc displays, but it uses a smaller fuel pump with a little bit different bypass jetting. Now, to illustrate going up, we've generated this data with another study in nozzles and jetting bypass combinations. And this is for, again, no boost. This is for a 3,000 horsepower goal. We're first going to switch to 2 atmospheres of boost on the way up. Now that's again a 1,000 cubic inch engine entry, about a little bit less than 4:1 air-to-fuel ratio. And it turned out we had to go to 2 rows of nozzles to get everything to work when we go to the higher boost. So in the no boost situation, we have just 1 row of nozzles. And then when we start going up in boost, we initiate a 2nd row of nozzles. In addition, we shut down 1 of 2 additional bypasses. We simply shut down 1 of them, and it would be the combination of shutting down the bypass and turning on a 2nd set of nozzles to get about a 4:1 air-to-fuel ratio for 2 atmospheres of boost. To go to 3 atmospheres of boost, we simply triple our engine size. And in this combination, we dropped out our last additional bypass. This particular combination started out with 2 additional bypasses. It progressed to 1 bypass, and then it progressed to none. The combination of no bypasses, 2 sets of nozzles, and 1,500 cubic inches of engine size give us a much richer air-to-fuel ratio, and for a 3,000 horsepower engine, an air-to-fuel ratio in the low 3s is probably necessary. We can expand this even further to 4 atmospheres, which would be a 4,000 horsepower motor or more. Could be as much as 5,000 horsepower. And this is done in 4 stages. This combination is done starting with our 500-inch engine with no boost, going to 800 cubic inches, and that is basically 1.6 atmospheres of boost. Then we go to 1,400 cubic inches, that's about 2.9 atmospheres of boost, and then we go to 2,000 cubic inches, that's 4 atmospheres of boost. All of these values were juggled to get all the jetting combinations to work in a reasonable profile. We started out with a 5-to-1 air-to-fuel ratio. With our second stage, we go to a richer 4.7 air-fuel ratio. With our third stage, we go much richer, 3.7. And our final stage, we go to a 3-to-1 air-to-fuel ratio. That would be typically how rich a 4-atmosphere boost engine would be. Examining how all this would work, we start out with a main bypass and 2 high-speed bypasses. They're called high-speed bypasses in ProCalc. And what we do is sequentially drop one out and bring in another nozzles and drop another one out in the 4 stages. In this second stage, all we do is drop out one of the main bypasses, and that gives us that enrichment that we were looking at up at the top. In the next stage, we bring in additional nozzles, so for 2 full rows of nozzles, and that gives us the next stage of enrichment. And then the final stage, we drop out the last additional bypass, and we're running on strictly a main bypass and 2 rows of nozzles, and everything's been adjusted for the 3-to-1 air-to-fuel ratio goal that we wanted. You'll notice that the second set of nozzles tend to be much larger than the first set of nozzles to get this combination. The bypasses, the additional bypasses, also tend to be very large values, but this is all easy to evaluate in virtual reality using the ProCalc calculator, and an entire jetting routine can be profiled ahead of time before parts are purchased, are assembled, and then are set up. The advantage of mechanical fuel injection in this combination, the advantage of ProCalc in this combination is you can go to very high outputs with a relatively simple fuel injection system, that is mechanical injection. This one involves simply 2 solenoids shutting a bypass off on one and another bypass off on another, and another solenoid turning on a set of nozzles on the other. So for 3 parts, 3 additional pathways, electrical pathways, you can accomplish the jetting profiles from idle all the way up to very high boost levels. It's conceivable that you could add more steps and go to even higher boost levels and compute all of the nozzles and the jetting ahead of time, again in virtual reality, and profile an entire engine combination. In our research, we've worked out a 2-cycle engine combination with 2 stages of supercharging, 1 supercharging and 1 turbocharging with extremely high boosts. And it's conceivable that you can be going to extremely high horsepower levels, approaching 10,000 and even beyond with straight methanol fuel. In addition to this, you can add nitro in ProCalc, and you can start out with small percentages of nitro to combine with turbocharging. And using enrichment, you can accomplish intercooling, fuel intercooling, to keep everything from melting down and continue to be going up in very high power levels. Thank you for your time.